Yeah, so my name's Neil Scott. I've been here at Queen's since 2005. Just a little bit about my background. I did my PhD work in basic sort of biogeochemistry, and you might say, well, what the heck is biogeochemistry? Basically what I did is study the kind of factors that influence the cycling of elements like carbon and nitrogen. And it turns out that those cycles are a key part of when we think about climate change and the things that are changing. Those two cycles at a global scale are pretty important. I took that knowledge that I acquired as a PhD student and I started applying it to things, and I went to New Zealand as a postdoc for 6 years, 2 years, well, a year and a half as a postdoc, and then I got a permanent job there, and I started to use this information on how these processes that control the cycles of carbon and nitrogen relate to doing things like how do you do an inventory of carbon for a country. And we developed systems for that country, which they're still using to some extent today for international reporting, because all countries are required to report on their emissions of all the major greenhouse gases, and also their sinks. Where are these gases going when they're taken out of the atmosphere and sort of incorporated into terrestrial ecosystems or into the ocean. And so I've done a lot of work on land use and land use change and how it influences these cycles of carbon and nitrogen and how they interact with the climate system. So what I'm going to do today is talk to you a little bit about mostly just some basic information. I think most of you will, I'm hoping everybody has heard about the issue of climate change at this point, has some sense of the evidence and information that's out there. I just wanted to review some of that quickly. But then I'm hoping to leave some time at the end. And I guess what I'd really like to do is to have, this can be more of a discussion. I don't necessarily need to sit up here and yak at you for an hour. In fact, I don't want to, and I don't have enough material to do that because I don't really think that's what we need to do. I think there's some really interesting issues that come out of this. And I'm going to start, this is my sort of my title. But I'm going to start by doing something which I sometimes like to do, which is to give you the conclusions first and the take-home messages. So in case we run out of time or I get yanked off the stage, you'll at least get this part. But this can maybe get you thinking as we go through, or as I go through some of these slides, about some of the important points. Okay? And so just to sort of hit these really quickly, the climate system is changing. And northern regions, it's changing more than it is in for example, in Canada, in other parts of North America, the rates of change are slower. The greatest rates of change, and you'll see some projections put onto a map, the northern areas are the ones that are expected to change the most and that already are changing the most. That's happening, okay? That's not, there's not really much debate about that. The data show that pretty clearly. So we've kind of moved beyond, well, how do we mitigate? How do we prevent this from happening to what are we going to do now that it's happening? And so we're kind of starting to think more about adaptation. And that's where I think engineering is really important, because that's going to be a key part of adaptation. What are the solutions going to look like in a whole new climate regime? And that's something that we can think a little bit about during the course of my presentation, then maybe talk about that at the end. How do we think about these problems and engineering solutions when we don't even really know what the background will be in terms of basic weather and climate? Okay? So that's one thing. That kind of ties into the changes are already occurring and they're already having impacts on northern communities. Social impacts in terms of the ability to hunt on sea ice, things like that, are all starting to change. And this is, I'm getting further north, and we always have to wonder, what do we mean when we say north? And I'm thinking of sort of northern Ontario up into where I do a lot of my work is up in Nunavut on Melville Island. That's high Arctic sorts of areas. But these communities are interspersed throughout all of this region. The future is uncertain. And I think that's probably the biggest issue, and perhaps thinking about engineering is how do you make decisions about what to do when you don't really know what the conditions are going to be like in which you'll have to apply an engineering solution. And I'm going to show you some projections based on various scenarios of emissions going forward into the future, and you'll see the uncertainty that's there. And it's still significant, and it depends in part on what happens from a policy perspective. And Warren, maybe my colleague over here, you're going to talk about some of the policy things, I think, right? So I'm not going to talk much about policy. I'm going to leave that to him. But it does create an interesting situation about applying solutions in an uncertain world. Okay? So we'll think about that a little bit. And then finally, this is partly based on listening to the discussion that we had yesterday morning about the, just skip my head there, you talk about, sorry, the first person yesterday morning. The residential schools. Thank you. He made a couple of points about the importance of traditional knowledge and knowledge that you can get from elders, and I think that's really important. And I think it's really important to think about, when I worked in New Zealand, we worked a lot with indigenous communities there, the Maori people. And anytime we went out and we were trying to sort of think about environmental problems and solutions for those people, we had to work with those people. And it's incredibly important to embrace that knowledge and to work with the people for whom you're trying to develop solutions, because I think otherwise, in many cases, it's doomed to fail. And that's just based on my own experience. Okay? So keep those things in mind, and we'll come back to some discussion points at the end and maybe follow up on some of these issues. All right, so the first thing I wanted to see, how many of you know what IPCC is? Okay. All right, not very many. So I'm going to be adventurous here and see how this will work. I've been trying to drag cursors all over the place and find my, darn. I wish you could just scroll it across or something. Aha, there we go. Got to go up to the top, right, there we go. I'm getting close. This is total challenge to my, okay. I'll never get my rest of my slides back, but anyway, I made it this far. So what is the IPCC? It's the Intergovernmental Panel on Climate Change, and it's a group assembled under the direction of the World Meteorological Organization, WMO, which is essentially charged with synthesizing information about climate change. And periodically they come out with reports. A lot of the slides and things that I'm going to show you today actually come from one of the most recent reports from the IPCC. The IPCC is kind of a unique thing in that, first of all, they don't do any research. Okay? They're synthesizing research that's out there. That's all that they do. And it's a body that can include up to 1,000 scientists when they actually put these reports together. So it's very much a group effort with multiple levels of evaluation and scrutiny, which all goes into producing these reports about what's happening in the climate system and what are the potential risks or impacts of those changes. And if you want to see, the reports are all online. If you'd like to go and look at them, there's way more information than what I'm going to present to you today. But this is the group. And there's been some criticism, especially when the IPCC first got going, about, well, they weren't really looking at all the information, they were biased and things like that. I think they've changed some of their processes, and personally I'm pretty confident that given the large number of people involved in this process, that it is a consensus building process and that the information that's presented reflects not the opinion of one or two people, but of thousands of individuals. They also have some fairly unique terminology, which relates to risk. And a big part of this whole thinking about engineering solutions is, what's the risk? And how do we assess risk? And how likely is it that something's going to happen? The IPCC has developed some unique terminology to sort of express whether something is likely to happen, highly likely to happen, might happen. They have their own special terminology that they've adopted to try and convey this uncertainty in non-quantitative ways. All right, now comes the next part of the adventure. Let's see if we can get back. And if you have any questions.
I guess one question then. Is there any link to quantifying somehow that probability of risk, or is it purely qualitative?
From what I've seen, Warren,
highly likely, or
you might know, to me it's all still like the highly likely, and they haven't put numbers like 95% confidence or anything to those predictions yet. And I don't think they will, actually.
It made, you know, the information, yeah. Because thinking from our engine, you know, we always try to.
Right, be quantitative. Well, I think everybody would.
We always ask in our examinations, okay, you're saying this, what do you mean?
What does it mean? I know,
What
it's exactly right.
A good agreement or a,
yeah.
Or highly likely, whatever it means. So.
Yeah, they've purposely avoided, you know, I think trying to do that because it's hard. I mean, and when you see the errors on the predictions, you can understand why it's pretty hard to put those sort of numbers on those forecasts. I just have to find my cursor again. Oh, there we go. Okay, you succeeded. Okay, so just, and this, I think probably people have seen what is responsible for this greenhouse effect, which is causing some of the changes in climate that we observe. And so one thing I'll start off by saying is that if we didn't have a greenhouse effect, we'd all be pretty darn cold. So we should be thankful that there is a greenhouse effect to some extent, because without it, we'd maybe be kind of like Mars in terms of our weather, and that would be a challenge, to say the least. So we should be thankful that there's a bit of a greenhouse effect. And what that means is that so radiation that comes from the sun comes in as shortwave radiation. It hits the Earth's surface. It gets re-radiated as long-wave radiation. Some of that long-wave radiation then gets reflected back to the Earth's surface. The amount of it that gets reflected back is, to some extent, dependent on the size of this greenhouse, if you will, which is made up of a series of gases. They're not all shown here, but these are the three major greenhouse gases. I've added one over here, which is actually water vapor. Water vapor is actually the major greenhouse gas in terms of what's responsible for reflecting this long-wave radiation, but it's not changing very much. And so it often kind of gets forgotten as a greenhouse gas, but it's incredibly important as a component of this greenhouse. What's essentially happened over time is that the size of this blanket, I like to think of it as a blanket that's around the Earth, has gotten bigger, or it's gotten thicker. You know, you have different blankets you put on when it gets colder or warmer, right? So it's kind of like, well, the Earth is putting on a little warmer blanket. Not intentionally, but as a result of the production of these different greenhouse gases, the blanket's a little bit warmer and it's holding the heat in more than it did previously. Just to kind of show you some of the data and information. So this is showing global surface temperatures going back into the late 1800s, all based on a 20th century average here. And basically these dark red bars, these are the warmest years. In fact, 2014 was the warmest year on record. And again, this is just going back to the time when record keeping actually started. I'm going to show you some older data related to temperature, but that's all based on proxies, or using proxy information to, if you will, reconstruct temperature data going back in time. But these are the current records that are actually available, and this just kind of shows the pattern. This deviation on the positive side really starting to occur in around the 1960s and 1970s. So just to put this in a longer time scale context, because it's important to remember that CO2 has changed in the past. It hasn't always been static. Temperatures have changed in the past. The Earth's climate is very dynamic. So it's part of the challenge now is putting the contemporary signal on top of that historical variability. And this is showing data going back 650,000 years. And this is really part of the basis for being concerned about the future in terms of what will happen. And what this shows is the relationship between CO2 concentrations, which are shown here in the bluish kind of bars. There's a couple of different records that are used here. These are coming from ice cores. And a proxy for temperature, which is the amount of a certain isotope of hydrogen. So this is a proxy for temperature. And what you can see is, going back through this record, those two track each other reasonably well over the last 650,000 years. And the interesting thing now is that here's where we are today, and in fact we're actually almost up to 400. We're up to 397. This was from a few years ago. first measurements at 400 parts per million were actually made in 2013. It was the first atmospheric measurement that hit 400 parts per million. So the key thing, and again, when we think about changes in climate, is the rate of change is unprecedented. Okay, and if you look at these, just the graph, here's where it's gone in this. I mean, it's if you saw Al Gore's movie, you know, he got on the conveyor belt or the conveyor chair and he lifted himself up to show everybody how high up the current level was relative to the past. And this, I think, shows it pretty well, is that the current levels of CO2 are well above anything that we've seen over the last 650,000 years. In fact, they're higher than they've been in the last sort of 3 to 5 million years right now. Just to look a little bit more at the contemporary data, so there's a monitoring station on the top of Mauna Kea in Hawaii, which has been the longest running atmospheric monitoring station globally. And they measure CO2 at a very high temporal frequency, and they've been producing data. Actually goes back a little bit further than this. It goes back into the 1950s. And you can see we've been on a pretty steady trajectory of increasing CO2 concentrations. Anybody know, so the actual data has this sort of sawtooth look to it. Anybody know why that is? Why doesn't it just keep going up straight? Anybody have an idea why that occurs? I like to ask questions. Yeah.
Cycles with the seasons.
Okay, can you be more specific? So you're right, you're on the right track. It has to do with seasonality. Think about where is it summer and where is it winter, and what's happening during summer and winter in terms of the CO2 in the atmosphere.
So yeah, there'd be more in the summer. It would be lower because there's more vegetation. So
Okay.
that would,
But there's vegetation in the southern hemisphere too. So when it's summer in the southern hemisphere, it's winter in the northern hemisphere, and then they flip-flop. So there's always some vegetation out there doing photosynthesis and taking CO2 out of the atmosphere. Why does it do this then? What's that?
Is there more on one side?
Yes, exactly right. So there's way more vegetation in the northern hemisphere than in the southern hemisphere. And so that's the reason, because of that, the seasonal pattern, but because there's not the same amount of basically photosynthetic tissue in the southern hemisphere as there is in the northern hemisphere. So that gives you that cycle. Okay?
Is the populations and human-induced CO2 also similarly? I thought it would be more concentrated in the northern hemisphere as well. Is that part of the measured effect? The fact that in winter season there's more heating and things?
Well,
or is it all the vegetation?
that's more a local effect.
So those are more local. And,
Yeah.
And so it has to do just with the vegetation.
Mm-hmm.
Okay.
Yeah. These stations ideally are sampling a pretty well mixed atmosphere. That's the idea of this one's out in the middle of the ocean, you know, it's in a remote area, and there's quite a few of these stations now around the globe and carrying out this kind of monitoring. But part of the reason for having them, and there's one up in Alert, I think, and so they're kind of scattered around, hopefully in areas that are somewhat more pristine and avoid those local effects.
And I guess also, even if we probably generate as much CO2 from cooling and things in the summer as maybe.
Yeah.
In the past, maybe it was the reverse, but certainly for hydro demand, it's
Right.
now reversed. The peak time is in the summer, whereas it always used to be in the winter.
Right. And the other thing I'll say is when you look at, and I don't actually have this number in one of my slides, I'm trying to remember exactly what the number is, but the magnitude of the removal and production of CO2 from natural ecosystems is much greater than it is from fossil fuel burning. So that's a small signal on top of this already fairly large movement of CO2 in and out of the atmosphere. But that's pretty much a balance. What goes up comes back in terms of natural ecosystems. It's pretty much in balance, but it's a big flux in both directions. Just to give you a sense of what the sources are for this CO2, and this is going back into, the late 1800s. During that time, land use change, which is this bottom bar here, this was the major source of CO2. Anybody have any idea what was going on in the late 1800s? What land use change was occurring, and why the heck was it producing CO2 into the atmosphere? Anybody have an idea? Yeah.
Burning a forest, creating farmland.
Burning a forest and creating farmland. And then what happened to some of that farmland?
Oh, it's turned into cities?
Well, it's turned into cities, but some of the tillage practices and the management practices were fairly intensive, and there's actually a lot of carbon stored in the soil. As a result of some soil degradation, a lot of that carbon got released to the atmosphere. So it was partly the burning, the clearing of land, but also some of the soil mismanagement that occurred during that time. So that was the big signature in terms of CO2, but then you can see here in the 1940s and 50s, the increased use of fossil fuels really pushed this signal up from that time going forward. And these are the different constituents in terms of fossil fuel, coal, oil, gas, and others, and how much they contribute to that signal.
What's others? Like what would that in that category?
There's some other, I don't know if that, because I'm guessing that this would include for like electricity is in here in terms of the other generation. What would others be? Is there one I'm missing, Warren? What would they lump into others? Oh yeah, there we go. Great. Oh, you're reading the slides. Excellent. That's good. I would have thought they would have put that in because coal is part of cement production, but they've separated it out. So
Secondary, but it's also the
it's big.
mining. It's the mining of those limestone and minerals because there's a big CO2 release, and when there's CO2 releases, you convert
Mm,
the limestone into the
Just-
actual clinker.
right.
So it's 5%.
Yeah, it's always been a big, cement making has always been a big number, and it's always listed separately actually, which is, but that kind of gives you a sense of the magnitude of the amount of production.
I'm a farm boy. What about agricultural? Like all the just agricultural practices?
Sit tight.
Okay.
So there are other components to this besides CO2, and the other two major, and I say major greenhouse gases that are changing are nitrous oxide and methane, and those are, especially nitrous oxide, is tied greatly to agricultural practices. So use of fertilizers, slurry management, things like that. A lot of that nitrous oxide comes from those practices. Okay, and so this shows again the changes in methane in the middle here. This is nitrous oxide down here on the bottom, and here's the CO2 number up here. These the older points here are again based on ice core data, and the actual atmospheric measurements for these gases are shown here in solid lines. So it's not just a CO2 problem. There are other greenhouse gases as well, and this kind of summarizes all these different sources or things that are contributing to this increase in greenhouse gases in the atmosphere. This is only going back to 1970, but the bottom bar here is essentially CO2 from fossil fuel use. This orange bar in here is CO2 from land use changes that are occurring, and some of those can be agricultural as well. The middle one here, the light blue one, this is methane. And then the top bar up here is nitrous oxide. Okay? And this is kind of interesting because these have all been adjusted so that they are expressed on what we call a CO2 equivalent basis. Each one of these gases have what's called a different global warming potential. And for example, nitrous oxide is the current number is right around 300 times more potent per molecule as a greenhouse gas than CO2. So a tiny bit of nitrous oxide production goes a long way towards increasing the size of that blanket over the Earth's surface. Okay? This adjusts them all so they're on a somewhat equivalent basis, so you can sort of compare how each of these different gases are impacting the overall greenhouse effect. Now, we have to be very, very thankful for the fact that we have some natural sinks for CO2. What do I mean by a sink? A sink is something that's basically taking CO2 out of the atmosphere and storing it on the Earth's surface. Okay? And so this just kind of breaks things down. And this slide comes from a project called the Global Carbon Project. They've got a lot of great material if you want to learn more about the global carbon cycle and how humans are disrupting that cycle. I'd suggest looking at their website. Anyway, so here are the main sources of CO2. This is industrial activity and fossil fuel use. Here's the land use change component. So you add those together, where does it go? Okay, and turns out a large chunk of it gets soaked up by the ocean. Okay, roughly a quarter of it gets soaked up by the ocean. Okay, about another quarter gets soaked up by the land surface into vegetation and into soils. The rest of it kind of ends up in the atmosphere. And that's what we see in that signal of increasing CO2. It's what's left over that ends up in the atmosphere. Okay? But you can just see if these go away, we're almost doubling the amount of CO2 that's going up into the atmosphere. Okay? So we should be very thankful for these sinks. We actually don't really know how finite they might be. And that's one of the things that I work on, is trying to understand the terrestrial part of this and what controls the size of this removal of CO2 from the atmosphere, and what's its longevity? Is it going to go on for another century, or is it going to disappear in 10 years? We don't know. Okay? Because this one's really hard to trace it directly to specific things. There's so many processes that are going on here, and each one contributes a little tiny amount to the overall number. It's very hard to sort of say, well, this particular activity is contributing this amount to the sink. Okay? So there's a lot of things going on, a lot of complexity, and a lot of uncertainty. Yeah?
So for these sinks, does it matter about geography? So if you have a lot of the generation plants where there's not much vegetation, does that mean that a higher percentage of that goes into the atmosphere? Or can you have like one area that's heavily forested in the world and other areas that, you know, on extreme, and then it'll still kind of go to those same? Does it get
right
up in the atmosphere and then it gets recirculated?
Yeah.
Or
Yes.
no?
Yes. So it goes into the atmosphere. This is a global picture. Okay. If you had a facility that was producing CO2,
local effects aren't viewed to be
not in this one, not in this one, but there are what are called mitigation projects, which are projects applied at local scales. Some company may decide they want to plant 1,000 hectares of trees to help to offset some of their CO2 emissions. And there's a whole range of work going on globally with sort of looking at these projects and trying to figure out how much carbon they're actually capturing. And that's the whole idea with like a like a carbon tax or a system like that, is that there's a financial incentive to reward people for taking CO2 out of the atmosphere and storing it.
So, but in terms of at least the knowledge of the mechanisms, that it would be equally effective to plant those trees close to where your plant is, or it could be the other side of the world and it would have
so the current
theoretically the same offsetting.
Yes.
Okay.
The way the system is kind of viewed now, it doesn't matter where those sinks are located. Okay, you can put them locally, or you can one of the projects that's being looked at, and I've got a colleague working on, are what are called RED initiatives. RED initiatives are basically reduced deforestation and forest destruction. And the idea is that if we can preserve tropical forests, which that land use, the current land use signal, this one right down here, is largely clearing of tropical forests, clearing and burning of tropical forests. If those forests can be protected and preserved, it keeps that carbon on the land surface instead of returning it to the atmosphere. And so there are projects, companies are investing in projects in Brazil and other countries to, if you will, try and get some credits for their own CO2 emissions by supporting these types of projects. This is just one, that's just one type. There's all sorts of examples of those going on around the world now. One of the interesting things I'll also say about northern regions, and I didn't put a map up here and I should have, but northern areas, if you look at northern Ontario, and as you move up into the Arctic, have some of the most carbon-rich soils anywhere in the world. Okay? And they're small areas, they're small pockets of largely organic soils, like peatland soils. I don't know if any of you have been on a peatland before and you've seen peaty soils. How many of you know what peat moss is? Okay, so peat moss is basically peat that's been mined and put into a bag so you can put it in your garden. It's really carbon rich compared to mineral soils. All right? And so there's some incredibly vulnerable soils which are largely frozen now, and I'll talk a little bit about permafrost thawing. Those soils kind of start to thaw. Some of that carbon that's been stored for thousands of years is suddenly available for organisms to use as a substrate. And if they do, then the CO2, the byproduct of microbial processes, goes up into the atmosphere. So that's one of the questions or issues right now in thinking about some of these northern systems, is what's going to happen to all that carbon that's stored in the soil if permafrost thawing continues. So just to show you a little bit, these sinks are not static, they are changing, and they've been sort of trying to keep up, if you will, with the increasing emissions. And so this is just a graph showing over here, here's the fossil fuel production of CO2, and here's the land use change. So here's the two production sides of that coin that I showed you on the previous slide. This one's actually been dropping a little bit through some improvements in forest management in some tropical countries. They've gotten a little better handle on things like illegal logging, so this number has started to drop. And here's the sinks. The ocean sink has kind of shown a steady increase. The ocean's been doing a great job. We got to keep encouraging the ocean. It's sort of keeping up to some extent with the increasing CO2 in the atmosphere. The land sink is much more variable. It's a little bit of an upward trend over the time period of interest here. This is only going back to 1960. And here's the atmospheric growth over that same time period. So, as I said, the sinks are helping tremendously. They're removing roughly half of the CO2 that's being produced. And they sort of seem to be keeping up to some extent. And when you look at the sort of residual part here, although this is rising a little bit, so they're clearly not quite keeping up at the same rate as the production is. Yes?
Is there concern about the sinks filling up completely?
Yes.
And spilling over?
Yes. and we don't know. I mean, so for example, in the oceans, and I have a couple of risk slides here I'll show you in a second. So what happens to the oceans? How do oceans absorb CO2? They're getting more acidic, so that's one way. And then how else?
Algae?
Yeah, so changes in productivity of the biota are removing some CO2 from the atmosphere. The acidification one is a big one, and so there's this equilibrium. If you've done some chemistry, you know there's this equilibrium between CO2 as a gas and CO2 that's dissolved in solution. If you increase the concentration in the gaseous phase, you can push more into the solution, and that lowers the pH because it forms carbonic acid. Okay, so that's happening at a global scale right now, and the pH of the ocean is, we're starting to be able to measure declines in the pH of the ocean at a global scale. So just in case you're not at all, or you're still questioning whether this is really a human-induced activity or not, I put this slide up here, and again, this is the IPCC's best assessment of the relative contributions to this, what we call greenhouse forcing. And so here's the observed warming up at the top, shown here with some uncertainty on it. The IPCC is really good about putting uncertainty estimates. This one actually is quantitative, so it's got an actual error bar on it. Here are the things that are contributing to this observed warming. So here's greenhouse gases and greenhouse gas production. It's a big bar, but there's a big uncertainty on it as well. Okay. There are other anthropogenic forcings which are actually going in the opposite direction to some extent. Don't ask me what all of them are, because I can't tell you what all of them are. Here's the combined effect of these two right here. And then here's a couple of natural forcings and natural internal variability. So these are really kind of the natural cycles that are going on that might be contributing some greenhouse gases to the atmosphere. And you can see their contribution is pretty small relative to the combined anthropogenic forcing that's occurring at present. And you can see that these come pretty close to being the same size bar. Okay, so that's kind of where we're at. Yeah?
Is the orange one supposed to be a combination of the green one and the yellow one?
I think so. It's interesting that the uncertainty bar goes down. It
Yeah, I mean,
shouldn't.
it's not done
No, it's not a
mathematically
quantitative.
correctly,
No,
I
no.
think. But anyway.
I knew somebody who had statistics would say that.
Yeah.
You can't, yeah, these errors are not, it's their way of putting some uncertainty on these estimates. So, okay, so what about looking ahead? So that's kind of where we're at right now. Okay, so let's just look ahead a little bit. And one of the things that the IPCC does is to put together scenarios. What might happen in the future? Because we don't know. We don't know whether suddenly we'll have drastic new policies that will reduce CO2 emissions. So what they do is a range of scenarios. And I think as much as anything here is to look at the uncertainties. Because this is where this whole issue of uncertainty, looking forward into the future, becomes important. Right? And so here, and if you look at these, they've sort of conveniently numbered each one of their scenarios. They have RCP 8.5, and they have a whole range of different emission scenarios. These are the sort of actually reduction in emissions here. These show the sort of targeted atmospheric concentrations of CO2 associated with these different emission scenarios. Okay? So the highest one is up here at around 1,000 parts per million. Remember, we're at 400 right now, 400 parts per million. So the worst case emission scenario that they're working with has it going up to around 1,000. Okay? The best case is that emissions stabilize at just over 400 parts per million, 430 to 480 parts per million. Okay? That's kind of their best case at this point of a scenario that they're working with. Okay? So what are the consequences of these different scenarios? And what they've done is kind of shown the extremes over here. So here's the potential impact on surface temperatures. Okay, the best case scenario here, which is RCP 2.6, shows a warming of about a degree at a global level. And we're already pretty close to that. The worst case scenario up here, which is RCP 8.5, shows a warming of around 4 degrees at a global scale. And you can see the uncertainty surrounding those estimates. Here are some estimates of potential sea level rise. So this is one of the consequences of warming, is there'll be an increase in sea level. It's interesting over time how this number, 10 years ago or so, there was some really sensational articles saying how there was going to be a 5 to 8 meter increase in sea level, and those numbers have kind of come down now a little bit, and now the forecasts look to be sort of the maximum would be around, this is a meter global increase in sea level. And best case scenario down here is about 0.4 meters. I put this up here. This is another way of representing the scenarios, but the main reason I put this up here is this one includes 3 points down here which extended beyond when the scenarios were initially generated. Okay, so here's where the scenarios sort of started to branch off, and what it shows here is that for these 2 periods, right now we're sort of following this worst case scenario. And this is just based on a couple years, a small amount of data, but it's a bit alarming that that's the trajectory that we, at least at this point, seem to be following, is the worst case emission scenario. Bless you.
Thanks.
Okay, so what are the consequences? And this is where I'll kind of finish up. There's all sorts of information in the IPCC about what are the consequences of these changes in climate that in some cases are already occurring and may become even greater in the future. A lot of this is thinking about risk. And when you think about what are the consequences and what are the solutions, you have to think about risk and how do you deal with this whole issue of risk assessment. And I don't know, do engineers, do you guys talk about risk assessment much and thinking about design solutions and things like that? Yeah, I think it's a key part of this, thinking forward, how do you design solutions, thinking about what the risks are and how do you assess those risks. And there's also uncertainty, and it's not always going to be quantifiable uncertainty. So how do you come up with solutions when you don't really know what the conditions might be in which your solution may be implemented? And that's a challenge, I think, going forward. So I'm just going to cruise through a couple of slides here. One of the things the IPCC is really good at doing is producing complex graphics that are really hard to read in some cases, I find. And this I found is a good example. There's so much information here, but what I want to really focus on, this is kind of looking at regional, so there's actually a world map behind here, looking at different regions and what are the risks. But I want to just focus on up here, this is polar regions, Arctic and Antarctica, and looking at, so these are different different scenarios of warming. So this kind of shows you the key over here. So the bottom bar is kind of the worst case scenario. The hatch part shows potential for mitigation. Okay, so if we are able to reduce CO2, there's a possibility of reducing these risks or these impacts by a certain amount. So with this one over here is risks to natural ecosystems, the little fish symbol there, and the terrestrial ecosystems. And so you can see, again, as the amount of CO2 produced goes up, the risk also goes up. Not too surprising. This is risks for health and well-being over here. And again, you can see there's potential for mitigation going on for these particular risks. But again, they tend to go up, although there's not much of a change between these last two scenarios. And finally, this one is unprecedented challenges, especially from the rate of change. So these are challenges to people and to society as a result of the rate at which the climate system is changing. Remember, I showed you before, that's really what's different about now, is that the changes are occurring much faster than they've ever occurred going back in geological time. Okay? And that's presenting all sorts of really interesting challenges in terms of thinking about risks and risk assessment. And I put this one up here mostly to remind me to talk about another risk, which is shown over here. And these are kind of color-coded. Again, as you go various emission scenarios, as you go up the axis here, more risk associated with higher emission scenarios, not too surprising. But the one I wanted to point out particularly here is the risk of extreme weather. Because extreme weather, and we are all hearing about, the severe droughts in California and all these other severe weather events. One of the predictions is that there'll be more severe weather events as we go forward. How do you plan for design of buildings when you don't even know what severe weather events might happen going forward into the future? How do you make those decisions? Do you over-engineer? I don't know. That's what the engineers have to decide. But that's one of the key risks that we need to think about. Here's just another way that the IPCC expressed risks. And again, it's looking at various emission scenarios, but I just wanted to point out what these are. So this is risk for terrestrial and freshwater species impacted by the rate of warming, okay, not just the total amount, but the rate of warming. This is risk for marine species, and this is really the ocean acidification. So here's acidification only, and here's acidification plus warming. So you put the two together, obviously the risks and the impacts become even greater. And then finally over here is risk for coastal human and natural systems impacted by sea level rise. A lot of these northern communities are right on the coast in many cases. And so what are the impacts of sea level rise going to be to those communities? Another thing to think a little bit about are reductions in crop growth. And again, what this is showing is over different time periods. Okay. Starting at 2010, going up to 2110, looking at whether crop yields are enhanced or degraded as a result of changes in climate. And what you see as we go further up this direction, we get greater and greater negative impacts on crop growth. There's also some interesting opportunities with this, because it may be that we'll be able to grow crops that normally now might only grow in the southern United States in Canada in 10 to 15 years. So some people say, oh, there's great opportunities. Okay, there may be. This is looking at sort of overall at a large scale, though, the expected reductions in crop growth associated with these scenarios going forward. This is a document just prepared by the EPA. It's kind of a summary. This is actually a bit more useful than a lot of these other complex IPCC graphs, just showing some of the important issues. And these are the things I think that we need to think about going forward. Health impacts, okay? Huge issues for for people living in northern communities, impacts on forests. One of the things I'm going to show you a picture of here in a second is fire, the importance of fire. Water resources, another really important issue, especially in areas that have permafrost, that have permafrost thawing. It changes water quality. Okay? What are the issues going to be associated with those changes? And so just to sort of conclude with a few things related to the north more specifically. So this is looking at predicted temperature and precipitation changes going forward into the future. They're different. So this is the worst case emissions scenario. This is the best case over here. And main thing I wanted to point out is the difference in terms of northern regions. And you can see that in all cases here, particularly for precipitation, but also for warming, these changes are going to be greater and occur faster in northern areas. Okay? And so those regions are going to be more heavily impacted than almost any other region in the world in the next 50 to 100 years. It's not that far into the future. Fires is a key one, and I'm not going to take time to try and drag all my screens across again, but this is showing just data from September 2015. This has been a huge fire year. Okay? And in the United States and in Canada, and if you look at the statistics on here, we're 10 to 15% above any sort of long-term running average, and in fact for area burned, it's almost 200%, I think it's the number was, higher than the sort of long-term average. That pattern may or may not get worse in going forward into the future. Okay? And then finally, to think about sea ice and changes in sea ice extent. And again, this is just showing some maps. The different lines up here are showing sort of the minimum and maximum amounts of sea ice for the last 20 to 30 years, I think. But again, the main point is that overall, we're looking at a reduction in sea ice in the Arctic and in northern areas. What's the impact of that going to be? Many communities, indigenous peoples that live in that area rely on sea ice for hunting and carrying out other activities. If the sea ice isn't there, what do they do in terms of traditional foods and things like that? Some of those sources may go away. So they're both social and ecological issues. And then finally, I talked a little bit about permafrost. Permafrost thawing is a real issue. In many cases, it can lead to these sorts of slope degradation events, thermokarst features. We've been studying some of these up on Melville Island where I do my work. These are kind of some larger scale than others, disturbances. Think about if you have a building on top of one of those and suddenly the top meter of soil just goes away and it all just kind of goes downhill. And this is sort of showing what some of these thermokarst features look like. Not necessarily on really steep slopes. Okay? We have a student working on how can you predict areas that might be vulnerable to these sorts of thermokarst degradation events. Okay, so I come back to my take-home messages that I started with. Climate is changing. We're moving beyond mitigation. We're thinking about adaptation. As engineers, you'll be part of that. How do we adapt to these new conditions when there's a lot of uncertainty? And I think that's an important issue to think about. These changes are already having an impact on northern communities. The future is uncertain. We need to embrace that uncertainty. We can't just sort of ignore it and hope it doesn't happen. I think it's important to embrace it and to figure out solutions that take into account the uncertainty that's present. And then finally, the importance of working with indigenous peoples to solve problems. I think I can't emphasize enough how important it is to work with the people to come up with solutions because those are the ones that will really gain traction and take advantage of traditional knowledge. There's a lot of knowledge that's out there which can help to inform engineering solutions, policy solutions, a whole range of activities that will be required in these northern areas. And we need to take advantage of that knowledge. Okay, so that's all I have to say. A little bit longer than I had thought, but so I just have a few questions and issues. And I don't know, Mark, if some of these, if they're of more interest to you or if they resonate more or if any particular ones are, I know, Colin, you had some interest in some of these issues. So, but I thought we've got a few minutes if anybody wants to just look at some of these. And I think this question of extreme weather. Okay? So how many people have heard of the concept of a 100-year flood? What does that mean?
Supposedly the worst flood in a century.
Okay, and what's that based on?
Previous data.
From the last period of time. Do those guidelines mean anything when we go forward? Because the situations, the extreme things that might happen weren't in that 100-year window of time when that 100-year event was defined. Okay? So we don't really even know. When we move into this area of uncertainty in terms of climate, do these historically constructed guidelines for flooding or other things, will they be relevant? And how do you design, if you're trying to engineer something related to rivers, you know, what do you use as your guide to then decide, well, how big of a berm do we need to build or whatever? If you base it on a 100-year flood, as we're seeing in many places now, it's not good enough, because more and more of these extreme events may make that 100-year time period over which a lot of this data was collected not as relevant going forward into the future. So how do you do it? What do you do? Uncertainty is a tough one. Anybody have it? How do you design something if you don't know the conditions that you're designing something for?
Well, it's the same
Don't
thing
laugh,
as
Andrew.
designing for earthquakes. It's
Mhm.
you take a risk. Somehow you, based on knowledge, and you take a risk.
Mhm.
And that's I guess a percent of uncertainty, and hopefully you're within a range of certainty.
Right,
Yeah.
right.
It is a good, because the earthquake knowledge keeps adapting and changing, and so we keep modifying our building codes.
Do they?
To
Okay.
assess that new, every time there's a major earthquake, that
Mhm.
more research and things are
Well, even
evaluated and
in
adjusted. Those have been the
earthquake
biggest changes in our building codes in the last 20, 25 years, I would say.
But even within that, I mean, there are all sorts of factors that are based on really things you don't understand.
Yeah.
You know, a certain factor that's stuck in there. But I mean, one of the big things in earthquake design is making it kind of very robust, and that there's lots of ductility so that things can, the big forces can. And so, I mean, I think one is coming up with certain designs that can, sort of adapt or, that are very robust, very resilient, knowing that those conditions can change. I mean, one thing I heard recently in a conference talking about risk, they said, structural engineers are very focused on, collapse, and the risk of it is actually really tiny. It's like 1 in a million or something is sort of the probability that we're using failure. Compared to, some of these environmental risks, are we too, obsessed with, this tiny little risk and sort of
losing track of
all
the
around us this much bigger risk.
Mm-hmm.
So, don't ignore that, risk of collapse, but there are these other huge risks around us that we should be
right.
thinking about as well.
They're harder to capture, and the earthquake one is interesting. I don't know. I mean, we haven't, I guess, had to expand the scale for earthquakes, right? Or have we? Are we still we're still kind of at the same scale? The Richter scale hasn't really changed.
Well, yeah, but the way in which we incorporate it into our
That's changed.
design codes has changed, and how we quantify whether or not. So the east coast of North America is now viewed as a seismic zone, whereas 50 years ago
It wasn't.
Would not at all. So you wouldn't do anything to mitigate against
Right.
earthquakes. And now we're saying no, you have to. Anything new, you have to design for it, and then
Mhm.
then you have to try to retrofit to. And so some of the same is still a lower probability, but recognizing it's not zero.
Right. Right.
And then it also goes to looking at the consequences too. So what happened in Christchurch and stuff. So from an engineering perspective, it was reasonable, but an economic disaster. And people are sort of saying, well, that's not our expectation that you would. But it did, from the engineer, it did exactly what structural engineers wanted it to do, but the consequences when it happens in a major city are vast from an economic perspective. That's not built into how we design structurally, because we're much more concerned about safety and not about economic loss.
Right. Right.
Yeah, I guess that ties into like the importance classes we call it in the building code.
But that's still all life safety.
Okay.
So it's all focused on life safety, not economic or property implications. The
But
same
isn't it
thing
like
with,
post disasters? Some of these buildings.
it's
have
still
something-
it's still life safety, right? No,
Okay.
the thing in Christchurch is the fact that the city got shut. You know, like
Yeah.
people can't do their daily lives after the fact, and then it just has such a huge impact on. So we had to, you know, I understand what you're doing, but we don't have those. They're all sort of, well, how can you? Will people live and survive through the disaster? Not that their lives are going to be reasonable afterwards. And so that's what the biggest, from the public perspective of Christchurch, was that you know, engineers didn't do what was needed because it affected their lives and livelihood. Because we haven't necessarily been designing for that.
So how do you design when you don't, like, I mean, let's think about water systems, and you know, how do you design a system if you don't, you know, whatever the conditions were that you based your design decisions on may be totally different in the future. So how do you do that? Do you over-engineer? Because there's a cost to over-engineering, right? Presumably, and so.
Well, climate change, it's a slow process. It's not going back to the earthquake where we associate catastrophic consequences. Where climate change, and you took a stand and indicated this is critical. We as engineers do talk about it. We take into account the consequences. Unfortunately, the politicians are not engineers, and there's an associated failure on behalf of those who make policies to understand the long-term consequences.
Mm-hmm.
If you were to say, and I come from Manitoba, and we did have 100 floods in 10 years. So we had several floods.
Right, good example, yeah.
And the consequences for First Nations, and yesterday we heard one of the presentations that a whole town was flooded, and the people were forced to live in hotels for 3 years. So the consequences are there, but are not catastrophic. And I think that's the message perhaps scientists like yourselves, have to bring to focus, that yes, these changes are coming, and these are the consequences.
Mm-hmm.
And when a few years ago, ice roads in Manitoba are usually take over 3 months, and in that period of time there were 3 weeks, and the government was forced to transport construction materials by Hercules aeroplanes, because there was no way to bring in food and materials to these communities.
Mm-hmm.
So I think there is some way scientists like yourself, as I said, to bring to light the consequences, especially for northern communities, and that's very important.
Mm-hmm. Mm-hmm. Yeah.
There's a whole new area of research that revolves around resilience.
Mm-hmm.
And that's the word that I don't think I've heard
Yeah.
being introduced here, which is why I'm introducing it.
I'm glad you brought that up, actually. That's good.
And I agree with you that, okay, the climate change issue is with us, but the timing of this is on a time scale that is measured in, for argument's sake, tens and decades, let's say. But it's the catastrophic and the prediction of catastrophic events that, whether that be weather, earthquakes, or so on, are still bedeviling us. But it's thinking about this resilience, is how a community becomes more resilient moving forward, recognizing what these threats are.
Mm-hmm.
Right? And it's going to be all over the map in terms of how a particular community will result. So you just look at New York City during Sandy. I happened to be there when Sandy struck. And in fact, the conference that I was at was canceled because the building got flooded. But it was the response of the city to this business of resilience moving forward. And I think as engineers, if we begin this process of trying to design communities or redeveloping communities, we need to keep that resilience component in mind.
Yeah, it's a key, right, especially for Arctic work right now. A lot of the discussion is around resilience theory and resilience of these systems, and trying to understand, how resilient are they going to be to these changes, and just kind of trying to make it, well, they're going to go from this state to this state, and it's a challenge. It's a hard thing to quantify. You're talking about sort of quantifiable frameworks, and capturing that uncertainty is a challenge. And I agree with what you're saying to some extent. I guess I think of, like people who lived in Calgary or in New Orleans and experienced these mass floods, whether that's large scale or whatnot. For those people, that was catastrophic. I'm sorry. and so maybe it's not at a global scale, maybe not as big a scale as an earthquake, but if those events, and they may not become more common. We just don't know. My feeling on this whole issue is, I think about risk, and I guess I come down to the side of, well, we actually have ways of moving away from some of the practices that are putting fossil fuels into the atmosphere, and I think you're going to hear about some of those maybe from Warren maybe later on, but we're not. We're just kind of continuing on, and why? I mean, maybe the changes won't be as catastrophic. We just don't know, but is it worth the risk? I mean, that's kind of where I come down on in thinking about these issues when we have alternatives the technology has moved forward quite a bit. And you talked about the problem with policy. I've decided that we can no longer depend on policymakers. They're just failing us miserably. But it makes sense to do things from an economic perspective and a resilience perspective. Those things make sense, and those are things that we can all do. We don't have to worry about whether the policymakers decide that, well, we should cut emissions by 10% or 1% or nothing. But we can all do things to try and sort of start to deal with this uncertainty that it's there. I mean, I don't think we can argue with that. That uncertainty is there, and we need to think about how to incorporate it into our thinking and our planning and our design as we move forward. So.
Well, excellent, Neil. Thank
Okay.
you very much.
Sure.